Mid-morning to you all. I'm Ben Seri, as you heard, and today with me is Yuval Sarel. Yuval, say hi.
Hey everybody, I'm Yuval. I'm a researcher in Ben's team.
I'm VP of Research at Armis, and we both work at Armis. Armis is an enterprise IoT security company, and we deal with IoT devices, unmanaged devices, in all kind of places, in corporates, in healthcare, in manufacturing. So part of our field is to understand whether these types of devices are really secure and whether they are limited to attacking only inside defined segments, or whether they can break segmentation, network segmentation, and do a lot of more harm than they were limited to in the first place. So this talk is about research that was actually published yesterday about 5 zero-day vulnerabilities that we've discovered in a protocol from Cisco called CDP. So it's called CDPwn. In a wide array of devices from Cisco, switches, routers, but also IP phones and IP cameras, somewhere between tens of millions or maybe more devices affected. So today we're going to cover at the beginning of the talk just about what did we actually find, what is CDPwn. As I mentioned, part of why we looked at this in the first place was to understand network segmentation better, to understand whether it's secure and whether we can poke holes at it. And so we're going to cover a bit about the history of VLAN hopping techniques. How are attackers doing this? What are the known techniques? And how does CDPwn come into that field and add something new? CDP is a protocol for Cisco. It's a layer 2 protocol that is used almost by every device that Cisco manufactures. And it's a proprietary layer 2 protocol. So we're going to cover a bit what are those types of protocols that exist in network appliances. Not only CDP, but a wide array of protocols that actually are a very large attack surface for in network appliances. This research, actually a bit like what Maddie talked about, started from researching vulnerabilities that were already closed, patches that might have not been as good as they should have been. So we looked at previous disclosures in various layer 2 protocols from Cisco, understood the underlying bugs that were fixed, and from there continued the research and actually found new vulnerabilities. So from that, a bit of about the implications of this research, what it means to the security of networks and enterprise-grade IP phones and IP cameras, and also if the live demo gods will be with us, we have an IP phone that we'll try to hack at the end of the talk. So to begin at a high level, what is CDPwn? So I said it's 5 vulnerabilities, but it's actually 4 remote code execution vulnerabilities and 1 denial of service vulnerability. It's in this protocol, in CDP. It affects a wide range of Cisco devices, switches, routers, IP phones, IP cameras, and an estimated number of around tens of millions of devices affected. And it's this huge group of devices that is affected from Nexus switches, which are the newest Cisco switches in the market, and Cisco IOS XR routers, certain firepower firewalls from Cisco, the entire range of new current Cisco IP phones, and a certain IP camera from Cisco as well, a series of IP cameras. These devices are used everywhere. The IP phones specifically are actually, I think, the most prevalent IP phones in the market. Cisco advertises that 95% of Fortune 500 companies use their IP phone solutions. And yeah, they are used in governments, in corporates. The White House, you can find them in the Situation Room, on the Resolute desk, throughout the White House. And then even when certain Israeli politicians come to visit, they are being listened to by 2 separate IP phones. Yeah, so they're really prevalent, but actually they are not the reason that we started this research. They were something that we found once we started looking and continued the research to other places. But as I mentioned, our initial goal was to see how VLAN hopping was done in the past and whether it can still be done today with additional vulnerabilities. So to understand VLAN hopping techniques, just to understand, we need to understand a bit more what is VLANs and how our network segments, how do they even work? So this is a simple design of a network diagram and how it should be done today. You would separate your devices based on trust level and based on types of device. So you might have one segment for low-grade IoT devices that you don't trust at all. They connect to the internet, but you really don't want them to interact with anything on your network. And then you would have a corporate segment with all your corporate assets, your computers, and whatnot, and so forth. And so the network would be split according to these segments in order to prevent devices from low-grade trust access levels talking to devices in higher trust levels. And so if an attacker were to compromise a device, an IoT device, for example, inside the IoT network, he can interact with other IoT devices, but he can't, by design, talk with devices in the corporate network or other parts of the network. So this is how network segments are supposed to be implemented. And what techniques existed in the past, or still in some ways exist today, to poke holes in that strategy. So double VLAN tagging is a very old technique. In some cases, it still works today. And it takes advantage of a simple flaw in how VLANs work. Each network has a native VLAN, the VLAN the VLAN number that would be tagged for any traffic that doesn't have any VLAN header. And the native VLAN number 1 is a very special native VLAN that means that you can send traffic inside the trunk port without a VLAN header, and that means this traffic belongs to VLAN number 1. So in a normal network where native VLAN number 1 is in use, and you have an attacker connected to a switch in an access port to the native VLAN, he can send packets without the VLAN header, and then on the trunk port, between the switches, it will also be without any VLAN header. And the switch also supports that the access port in the native VLAN does have a VLAN header with a native VLAN ID, number 1, but then the switch will peel off that header and send, again, the packet without any native VLAN. So the double VLAN tagging attack simply works by an attacker putting 2 VLAN headers, the outer one, a native VLAN, and then the inner one, any VLAN number that he'd like to be routed to. The switch will peel off the first native VLAN header, and then on the trunk port, the packet will contain the target VLAN. So this is a simple technique. It works, but it has limitations. First of all, you can only send packets one way. You will not receive packets back from the target VLAN. And it's also very it's simple to fix this. Cisco, for example, just says you should not use native VLAN number 1, and then this problem can't exist. But in certain cases where switch configurations are not ideal, this can still occur. Then another vulnerability or kind of a logical flaw was published, I think, maybe 5 or 10 years ago in a protocol called DTP. DTP is a Cisco protocol. It's also a proprietary protocol, the dynamic trunking protocol. And this protocol is a simple one. It's just meant for the automatic configuration of switch ports. So the ports of a switch will either be access port or trunk port, but DTP enables the port to change its mode from an access port to trunk port automatically by negotiating over DTP messages. So if DTP is not turned off, an attacker can simply send a malicious DTP or just send a DTP packet that says to the switch, move my port from an access port to a trunk port. Once that port is a trunk port, now he can send any packets for any VLAN. So this just abuses a feature in the switches that allows devices or switches to change from access port to trunk port. And here also a very simple solution. DTP should be turned on, off, should be turned off on all of the ports in access ports. Okay, so if DTP and double VLAN tagging can't be used, what can attackers still do? What they can still do is look for vulnerabilities in whatever layer 2 protocols are parsed by the code inside the switch. And CDPwn is vulnerabilities in exactly that type of attack surface. So we will get to the vulnerabilities in a minute, but again, if the attacker has something like CDPwn, how would he use it? So if he, for example, has code execution in a certain IoT device, he can send maliciously crafted CDP packets that will be parsed by the core switch. And if a vulnerability exists there, that might lead him eventually to code execution. And from the switch, obviously, he then has access to the entire network, all the VLANs. A core switch is a very strong position for an attacker to be in. He can exfiltrate data from the switch. He can listen in on any network traffic that traverses through the switch. He can carry out man-in-the-middle attacks. So other than VLAN hopping, which is what we started at, just attacking the switch is a gold mine of its own. So I mentioned the fact that DTP, for example, is a layer 2 protocol that has the logical flaws that allow you to move from an access port to a trunk port, but there are actually it's not one protocol. There are many of these layer 2 protocols that are used by network appliances, by switches and routers. The orange ones are proprietary ones from Cisco, but Cisco is the de facto standard in networking appliances, and so an attacker can consider all of these protocols as potential attack surface for him to try to poke at. What you see in the blue is the multicast addresses, the MAC addresses, and the Ethernet destination header to which these protocols are sent to, and the switch will listen in on any packets that are destined to these MAC addresses, and then parse the protocols accordingly. Okay, so as I mentioned before, we started, once we understood this attack surface, first of all, we wanted to learn what was found in the past in any of these protocols. And Cisco did publish 2 advisories that we found in 2018 regarding vulnerabilities in 2 protocols. One is the link layer discovery protocol, LLDP, and one is in CDP, in Cisco Discovery Protocol. And we thought, let's start by learning these protocols, learning these advisories, understand what was fixed, and see if we can find anything new. So a bit of an overview about these 2 protocols, CDP and LLDP. They are simple protocols. They are discovery protocols meant their main functionality is for devices to discover one another in a network. And they're almost similar in functionality, CDP and LLDP, only LLDP is the standard protocol, and CDP is Cisco's version of LLDP. They work by devices simply sending packets, advertising packets over a designating multicast MAC address, and then the devices that are connected directly to them will listen in on these packets and register in the local database that they have what are the devices that are connected directly to me. And these specific packets won't be forwarded inside the network by switches and routers. So whenever a switch accepts or listens to a CDP or an LLDP packet, that packet will be processed, but it will not be forwarded down the line to the rest of the network. And both of these protocols on the majority of the devices that support them are enabled by default. And CDP specifically also has advanced features that are using CDP not only for its discovery purposes, and for that reason, in these devices, CDP can't be turned off, or if it can be turned off, it will hurt the functionality of the device. So VoIP phones, for example, these have 2 Ethernet ports, and you can connect one of them to the network and then another to a computer, so kind of daisy chaining the network like that. And this feature for network segmentation to allow networks to be still segmented for VoIP phones and computers separately, the VoIP phones actually receive over CDP what is the VLAN designated for the IP phones and what is for the PC, and then the VoIP phone is also like a mini switch that separates these two segments. In addition, VoIP phones, for example, are powered with power over Ethernet, and they negotiate the power level that they'd like to receive from the switch, also using CDP. So CDP was not meant for this originally, but nevertheless, today it's also used for these features. Okay, so we started our research with this first advisory, and it said something very generic about the vulnerability that was closed. It said the vulnerability exists due to improper handling of malformed LDP messages. Sounds like every bug in every protocol. So nothing that you can actually work with. But what we did, we just downloaded the images of the affected IRS XR routers before and after the patch, and we used patch diffing. This is just a screenshot from Diaphora. It's an IDA plugin. So you can see there are many, many code changes between these two versions. Most of them are not related to the vulnerability that were fixed. We narrowed in on the function that parses specifically the type length value elements inside the protocol, which are complex structures that from time to time might include bugs. And in fact, yeah, this is a function that parses TLVs, LDP TLVs, and you can see in the green there that they added a lot of new boundary checks that didn't exist before. So this looks like the whole lot of bugs that were fixed here. We looked at each of them, but what we saw is that these were not RCE vulnerabilities that were fixed. There was either information leaks or denial of service vulnerabilities due to integer underflows that led to a wild copy onto stack or to heap. So nothing that could be exploited, or not that we saw how, but still vulnerabilities that we understood. And again, what we saw from this is that the type of bugs that they were being fixed, that they were fixing, are all sorts of boundary checks. So we continued the research to the second advisory. This sounded much more promising for an RCE. It says, insufficiently validated CDP packet headers. That sounded like something. It said a successive exploit could allow the attacker to cause a buffer overflow that could lead to remote execution. So that sounded good. And actually, the vulnerability, we did the same process. We did the patch diffing. We narrowed down on the parsing of TLVs. And one of the more complex TLVs in which we actually found the bug was the addresses TLV. So this is just part of a CDP packet. It has all these fields, but then it has these arrays of type length value structures. And the addresses is simply an array of IP addresses that this certain device that advertises itself has. But as you can see, there are way too much length fields in this TLV. It has the 2 bytes length for the entire TLV, and then a 4 bytes integer for the number of addresses in the array, which doesn't make any sense because one is limited by the other. And then for each of the addresses, there is the protocol length, which says whether this address is an IPv4 or IPv6. But although these addresses have fixed length of either 4 bytes or 16 bytes, there is still also an address length. There is an overcomplication of the structure that looks like it would be difficult to parse. And you would imagine what would happen if an address with this large buffer would be sent, although it's an IPv4 address for some reason with 132 bytes of length. Yeah, so we did find a heap overflow, a one-day heap overflow in CDP here, and I just want to walk through a bit of this specific vulnerability and how it works. There are actually more than one bugs in this code. The number of addresses that I said before is 4 bytes, for example, can be overflown because there is a multiplication there in the beginning. That's not the bug I want to talk about. There is, as you might notice, an interesting main copy at the end of the function that looks like it might be copying an address based on this large address length. So let's see if we just send a packet with a large address, whether it will cause an overflow. There is a device record. This is a structure that represents a certain CDP neighbor, a certain CDP device that is connected and sends CDP packets. That is allocated for each CDP neighbor, and inside it is an address blob for all the addresses that has been parsed. So initially, every time a packet is received, this address blob will either be allocated or be reused from a previous allocation. So in this packet, we have IPv4 address, but the address length is not of 4 bytes, so the protocol type inside the address blob will not be set, and it will remain uninitialized. And when we get to this if below, in most cases, it won't be IPv4 or IPv6 because it's uninitialized, and this memcopy won't occur. But as you might have understood from what I already described, there might be a state confusion here, and the protocol type might have already been set in a previous run. So this is how to exploit this bug. An attacker can send 2 CDP packets. The first one is a legitimate packet with an IPv4 address of 4 bytes. So an address blob would be allocated, and then this condition would be good, and the protocol type would be set accordingly. And then a second packet can be sent, this time with an address length that is large, but the same number of addresses. So the address blob will be reused, and we won't enter any of these ifs, but the protocol type being set in the previous one would already be IPv4, and then the memcopy will occur. So this is a heap overflow with attacker control data. Sounds pretty exploitable, and an attacker can also trigger this multiple times. Okay, so we understood that CDP is a good target. It has these complex structures, a TLV with all kinds of these length fields, and we also know from the LDP case, boundary checks are an issue with some of Cisco's code here. We feel that 0 days are closer than ever, and then we start our own 0-day research, and we want to CDPwn all the things. And we'll start now with one of the 0 days from Yuval. Okay.
Okay, so let's dive into some 0 days. So the first one is actually in the same TLV as we've just seen the issue with. It's got to do with the number of addresses field. As we said, it's 4 bytes long. This doesn't make a lot of sense because not only a packet cannot be that big, but the system is actually 32-bit, so the entire memory cannot hold so many addresses. So let's see what's the issue is here. So we're gonna want to cause a denial of service. We can allocate using the number of addresses field, but there's a length check using the number of addresses times 5. This multiplication can cause integer overflow. So let's see how we can leverage that into the desired denial of service. So the first try, we're gonna put max uint in the number of addresses, but then of course it's gonna overflow into too big of a number, so we won't pass our length check. Then we're gonna try to take a uint divided by 5 and round it up. So the multiplication is gonna give us a small number, which is reasonable to pass the length check, but the allocation size is gonna be too big. So the malloc is gonna fail and the resources will not gonna be allocated. And there won't be any denial of service. But we've seen this number works, so we're gonna multiply it by 4. Once again, the length check is gonna pass because we're still gonna get a small number. But the allocation is going to be with a reasonable size of 800 megabytes, which is going to be allocated, and shortly after the switch is going to crash due to resource exhaustion. So we got our denial of service. Okay, so let's check out the next 0 day. This 0 day impacts NXOX switches, and it's in the power request TLV. This is a fairly simple stack overflow, and it's exploitable, and we've managed to successfully exploit it due to no stack canaries and low entropy ASLR. But also this bug is a write what where, which we're gonna see how can be leveraged right now. So this is a copy loop, a while loop. There is virtually no length checks, you only take the length from the packet. and it's copied to the stack, to the temp buffer, which is a fixed size, so you can pretty much write whatever you want, how much you want into the stack. But as you notice, there's a variable called A1, which is also on the stack, and it can be run over, and it's being dereferenced and written to. So let's see step by step how we can do it and cause a write what well. So on our left, we have a simplified version of the code, and on our right, we have a memory map. On the right side of the memory, we have the packet being sent. On the top left, we have a simplified stack frame, and on the bottom left, we have the memory region around the address deadbeef. Our goal is to write cafe into the address deadbeef. So let's do it. So the first step, we're going to write the first D word into the first cell in temp, and we're going to increase the counter. This is fairly simple. The next steps are pretty straightforward. And here, we would have expected a length check to get us out of the loop, but as you can see, there is none. Next, we're going to write on A1 the address deadbeef minus 12. Then we're going to write to address deadbeef minus 4 the same address. This is minus 4 because you need to add a counter, and this is why you put minus 12, just believe me. You can compute it on your own. But this is like a side effect of the write what where, so if you want to exploit it, you need to find an address that you can write the previous D word to. Next step, we're going to increase counter again. We're going to write cafe into the next stack variable, let's call it stackvar. And after that, we get our desired write what where, cafe into the address deadbeef. So as we said, we were able to exploit it, and there's a nice trick that helps the exploitation. As I said, there is ASLR, and the system is 32-bit, but the ASLR is only 1 byte. It's somewhere in the middle of the address, so the distance between each ASLR option is only 4 kilobytes long, and the entire memory map is shifted with the same offset, meaning 2 libraries that are on the memory, or all the libraries are being shifted with the same offset. So if you put the numbers together, every library with 1 megabyte of text section is going to have overlap between the options of the ASLR. So the same addresses can be found to be mapped to code. So what we did is we used that to find multiple ASLR options and construct a multi-option rope chain. So one attempt to take an exploit is going to work on multiple ASLR options, giving us the ability to exploit in minutes instead of days when trying all the possibilities. We're not going to elaborate about this right now because it's how we actually did it is fairly complicated, but we're going to release a white paper in the future explaining just how this works.
Yeah, so we have a short video just showing how this was exploited on a Cisco Nexus switch. I do want to add something that we forgot to say. This ASLR bypass technique, but also a large part of this research was done by a coworker of us, Barak Haddad, who is not here, he's skiing. Yeah, so let's see what the demo looks like. Corporate laptop on one segment, and then the attacker is connected to another segment. And initially, we can see that the attacker tries to try to access the corporate laptop, but as I said, they're segmented, and he can't. He uses CDP just to find whatever port he's in and the VLAN number that he's in. He's going to use that after the attack. And so a lot of the magic happens inside this Python script, but essentially it sends multiple of these CDP packets, and it triggers the overflow multiple times. Certain times it will fail, the CDP daemon will reboot, but then he eventually reaches code execution. He will add a username for himself, a user and a password, and set it as an admin, and also add a management interface for the VLAN that he is in the VLAN number 2. And then he can connect with SSH, and the user that he has is also root, because the CDP daemon runs as root, and he can add that credentials. In the configuration of the switch, he can then move his own port to the corporate VLAN or the super secret VLAN in this terminal, and Once he's done that, obviously, he will be inside the same network as the corporate laptop. He can then access the corporate image in that file. Okay.
Okay, for the last 0 day for this talk, we're going to talk about a 0 day that affects multiple models of Cisco VoIP phones. This is also a fairly simple stack overflow. It's a mem copy to the stack without any length checks. And we were also able to exploit this bug, and due to the same lack of memory mitigations we've talked about earlier. But this specific device has another bug, enabling the attacker to attack any VoIP phone in his LAN. So as we said, CDP is usually sent with a multicast address, and this means that packets are only parsed in the neighboring devices. So when a computer sends a packet, a CDP packet to the switch parses it, but it doesn't pass it along. Then again, if an attacker or anyone wants to send a CDP packet with a unicast destined to the VoIP phone, he sends it to the switch, and the switch passes it along, but it shouldn't be parsed. But as I said, there is a bug causing it to be parsed, and allowing the attacker to use unicast or broadcast packets to attack any device he wants to in the switch. So let's see why that is. This is a graph showing the flow of a CDP packet inside the phone. The only two things to look at here is the red part, which is the function that has the 0 day we've talked about, and the green part, which is the function that validates the packet and makes sure it's a valid CDP packet. So if we take a look at the packet right now, we can see that the only verification of the Ethernet header is of the source MAC and not the destination MAC, meaning you can send it with any address you want as long as it gets to the switch. It's going to be parsed as a CDP packet, and if it has a 0 day, it's going to be, it could be exploited. So now after exploitation, which we're going to skip, we have some stuff we want to do with the VoIP and see what we can do once we gain this code execution. So as we said, the VoIPs can be found in really important places, and we like GIFs. So let's take a look at what we can do. So this phone has a Linux system with BusyBox and runs over ARM Little Endian, which gives us a lot of space to do whatever we want. A lot of stuff are already documented. And it has a nice screen, so we want to see what we can do with this screen. So we found this utility called FBCTL, which pointed us to understand that this device uses a frame buffer as a graphics driver. So as you can see on the right side of the slide, how this communication with the hardware actually works. So on the bottom you have the hardware, the screen itself, and in the middle you have the kernel, which implements a spatial driver to communicate with the hardware. And the interface it gives to the user is the device FB0. But usually the user space has an X server or an application of some sort that helps it to communicate with the frame buffer. In our case, we didn't have that, and cross-compiling it and running it on the phone was a bit of a headache, so we needed to work directly with the frame buffer itself. So whenever we try to write to the screen, this happens, like this sort of flickering, we're not being able to take over the screen. And this is due to the screen being busy written by another process. So what we're going to do is going to send sigstop to that process, just stop it, because we had a root privileges code execution, and we're going to use that utility FBCTL to draw some shapes on the screen, and maybe add some other shapes. And if we try a little bit harder, we can put some more elaborate images, like this one, and we can have a closer look. So now we're totally owning the screen. We think, yeah, maybe we had enough. We did enough for this device. But then we thought we want to be serious researchers. So the obvious next step is we're going to run some Doom on this device. So the first thing we do is go to Google, look for frame buffer doom, and we find someone already did some adaptations to make it work with frame buffer, and it was nice enough to put it on GitHub. And with some adaptation of our own, we were able to run doom on this device. Yeah. But we actually want to play it, and this doesn't have a keyboard, but it has keys. So what we do, we look for GPIO-like functionalities on the VoIP phone, and we find this LED CMD, which sounds like it has something to do with GPIO, and it uses this shared object called libIO API. This has this amazing function called keypad event, and it uses a device called input event 0, and this is actually documented in the Linux kernel documentation, so we're able to just use it as is. So now we're going to see a live demo, hopefully.
Okay, so we already ran the exploit just before the talk, so we can see the couple of CDP packets, and the CDP packet on the bottom is the one that triggered the exploit. You can see all this buffer, and if Yuval scrolls a bit, you can see the commands that he put there in the shellcode. And on the left is where he ran the exploit on the terminal. And so hopefully this VoIP phone already has the backdoor on it, and it communicates with Yuval's computer to give it any commands. So we can now see what the phone looks like when we do all kinds of things with it. The sound is from the phone call. And here we start by showing the exploit. The attacker can blink the LEDs and also record the call. You can see how bad we are at Doom. But, another part that we show you in the end of the video is that because we can also trigger this with a broadcast packet, the attacker can send one packet and it will crash all the VoIPs in the same LAN, in the same network. Okay. Okay, good. Right. So the live demos were not with the live demo gods were not with us, but this does work, and these vulnerabilities are real. I think part of the takeaways here, going back, are first to network segmentation. The IP phones obviously are important, but we started this from understanding whether network segmentation is a solid solution or whether holes can be found in it. And yeah, I think part of the takeaway is it isn't a bulletproof solution. It's not enough only to have segments the network. You need to also understand whether devices are acting out of place, and network switches are also endpoints in a way. There are also embedded devices that can be taken over. The second bullet, I think, is what do we now know about layer 2 protocols? There are many of these. It's a very large attack surface. CDP and LLDP are only 2 protocols. There are maybe a dozen of these. So it's an untapped attack surface, and much more research needs to be done to understand vulnerabilities in that place. And lastly, but most importantly, whenever you're bored in some meeting room, in a conference room, Doom on a Cisco IP phone is probably the best solution of your time, best use of your time. And if anybody have questions, I don't think we have microphones, but if you have any questions, then maybe we can try and answer them. Sure, do that. No. And The question was whether CDP is parsed on an interface in which CDP is disabled. So the answer is no. Yeah, the mitigation for this, prior to, if you can't patch, you can simply turn off CDP. But in certain devices like the IP phones, for example, it's almost impossible to do that. It's very difficult to turn off CDP. All right, thank you guys.